Hello, in this lecture we will prove the equation of Stewart's theorem. This is the equation of Stewart's theorem. In a nutshell, Stewart's theorem yields a relation between the side lengths of the triangle and its CVN. The CVN on triangle ABC is line segment AD. It is actually a line segment that exits from point A, that is the vertex of the triangle, and it will fall in any point along side BC. To the opposite side, from vertex A, it joins the opposite sides of vertex A, that is to say, vertex from point A, vertex A will join point A, will draw a line on the opposite sides of vertex A, that is to say, side BC. So here AD is the CVN. Okay, so Stewart's theorem yields a relation between the side lengths of the triangle, that is to say, side AC equals to B units in its length, side AB equals to C units in its length, and side BC equals to A units in its length. So those are the sides of triangle ABC, and the CVN in this triangle ABC is AD. Okay, the definition of a CVN, it is line segment that exists from the vertex, from vertex A, and ends at the opposite sides of vertex A. The opposite sides of vertex A is side BC. Okay, so here AD is the CVN of triangle ABC. So, and according to Stewart's theorem, B squared times M is the length of line segment BD, plus C squared times N is the length of line segment DC, equals to A is the length of side BC in triangle ABC, and we open the brackets here. Inside the brackets we have D squared, that is the CVN, the length of the CVN AD squared, plus M times N. M is BD, the length of side line segment BD, and N is the length of line segment DC. Okay, so in order to prove this equation, we will do a construction from point A. We will draw perpendicular on BC. Okay. So this angle equals to 90 degrees, and this angle equals to 90 degrees. According to our construction, we will define the touching point of the perpendicular from A on BC as E. Okay, we will define side AE or line segment AE as H. We will define line segment ED as X. Line segment, that is to say, line segment AD equals to X units in its length. And what is the length of line segment BE? From the drawing, it is very easy to see that the length of this line segment BE is equal to BD minus BE. BD minus ED, again, BD minus ED equals to BE. Okay, BD minus ED equals to BE. BD equals to M units according to what is given us here. Here BD equals to M units and ED equals to X units according to our definition. So in total, BE equals to M minus X. M minus X. Here, side line segment EC equals to X plus N. EC equals to X plus N. Okay, so in the next step, we'll implement the Pythagoras theorem on the green triangle AED. So, according to the Pythagoras theorem, in the green triangle AED, according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars in any right triangle. So in the green triangle AED, according to Pythagoras theorem, right now by PT is a version for Pythagoras theorem. The hypotenuse is AD, therefore the square of the hypotenuse is AD squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE squared plus ED squared. Repeat again, according to the Pythagoras theorem, in the green right triangle AED, AD squared equals to AE squared plus ED squared. So AD, the hypotenuse AD equals to the units in its length. Therefore, the square of the hypotenuse is D squared, and it is equal to AE squared. AE equals to H according to our definition. Therefore, A squared is H squared plus ED squared. ED equals to X according to our definition. Therefore, ED squared is X squared. In conclusion, we found out that according to the Pythagoras theorem, in the green right triangle AED, D squared equals to H squared plus H squared. Okay. In the next step, we will focus on the right triangle AC. In the right triangle AC, we will implement the Pythagoras theorem. According to the Pythagoras theorem, in triangle AEC, this triangle AC, the square of the hypotenuse is AC squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AE squared plus EC squared. I repeat again. According to the Pythagoras theorem, in the right triangle AEC, the according to the Pythagoras theorem, AC squared equals to AE squared plus EC squared. Okay, so this is the question number 1. So AC, the hypotenuse AC equals to B units, therefore AC squared is V squared, and it must be equal to AE squared. AE is h, according to our definition, therefore AE squared is h squared plus EC squared. We have already found out that EC equals to x plus n. Here EC equals to x plus n. Therefore EC squared is x plus n squared. So according to equation number 1 in triangle AEC, according to the Pythagoras theorem, we found out that b squared equals to a squared plus x plus h squared, x plus n squared. Repeat again, b squared equals to a squared plus x plus n squared. Here we'll open the brackets of this equation, equation number 1, and we'll get that according to equation number 1, b squared equals to h squared plus x plus n squared equals to x squared plus n squared plus 2 times xn. We have already found out that h squared plus h squared, h squared plus x squared equals to d squared. So we can substitute h squared plus x squared in this equation, equation number 1, by d squared. We'll do it now, and we get that b squared equals to h squared plus x squared is d squared, according to this equation, plus n squared plus 2 times xn. So this is equation number 1. In the next step, we'll focus on the right triangle, triangle ABE. I repeat again, we'll focus on the orange, on the pink triangle, triangle AEB. Okay, and we'll implement the Pythagoras theorem in this pink right triangle, triangle AB. According to the Pythagoras theorem, in the right pink triangle, triangle AB, here by PT evaluation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the circles of the perpendiculars. The hypotenuse is AB, therefore the square and AB, and so the square of the hypotenuse is AB squared, and it must be equal to the sum of the circles of the perpendiculars, that is to say, it must be equal to BE squared plus AE squared. BE squared plus AE squared. Repeat again, according to the Pythagoras theorem, in the right pink triangle, we get that AB squared equals to EB squared plus AE squared. Okay. It is given us in the question itself that AB equals to C units, therefore AB squared, so AB is C, so AB squared is C squared, and it must be equal to BE squared. BE is M minus X, therefore BE squared is M minus X squared plus AE squared. AE equals to H according to our definition, therefore AE squared is H squared. In conclusion, we found out that according to the Pythagoras theorem, in the pink triangle ABE, C squared equals to A minus X squared plus H squared. Here we'll open the brackets of this equation, equation number 2, and we get that according to equation number 2, C squared equals to A minus X squared equals to M squared plus X squared minus 2 times MX plus H squared. Okay. We have already found out that X plus H squared or H plus X squared, doesn't matter, equals to this square. So here we have X plus H squared. In this equation number 2, so we substitute X plus H squared by this square. Okay, according to this equation. And we get that according to equation number 2, C squared equals to M squared. X plus H squared is this square, so we substitute X plus H squared by this square minus 2mx. Okay, so we have here two equations. According to equation number 1, we found out that b squared equals to d squared plus n squared plus 2nx. And according to equation number 2, we found out that c squared equals to m squared plus d squared minus 2 times mx. In the next step, we will multiply equation number 1 by m, and then we will multiply equation number 2 by n, and then we will add the two equations together. This will give us equation number 3. So equation number 3 is the multiplication of equation number 1 by m, then the multiplication of equation number 2 by n, and then the addition of equation number 1 to equation number 2. This is equation number 3. So according to equation number 3, we'll get that m times, in equation number 1, we have d squared plus n squared plus 2nx. So we multiply equation number 1 by m. In the next step, we'll multiply equation number 2 by n, and we'll add the equations with each other. So equation number 2 multiplied by n is n times m squared plus d squared minus 2 times mx. Repeat again. We multiplied equation number 1 by m, we multiplied equation number 2 by n, and then we add the two equations with each other. So if we finish with this side of the equation, in the other side we also have to multiply equation number 1 by m. In the other side of the equation number 1 we have b squared, so we multiply b squared by m times b squared, and we'll multiply equation number 2 by n, the other side of the equation number 2 by n, so it is n times c squared, and we add the equations together. So on the other side of the equation number 3 we have mb squared plus nc squared. So in the next step we will open the brackets here in this side of the equation, and we will get that according to equation number 3, md squared plus mn squared plus 2mnx plus nm squared plus nd squared minus 2mnx equals to, on the other side of the equation we have b squared m plus c squared n. Okay, so this is what we got. This is actually equation number 3. I repeat again that equation number 3, we got equation number 3 by multiplication of equation number 1 by n, then we multiplied equation number 2 by n, and we added the two equations together, and we got this equation. This is the result, equation number 3. So here we have 2mnx plus 2mnx minus 2mnx is 0, of course, so we'll delete, cancel the two expressions. So what is left from equation number 3 after we cancel the two expressions? We have here, we take this square as a common factor. We take out this square as a common factor. So here we have md square. So this square is a common factor. So what is left from md square after we take this square as a common factor? What's left is m. Okay, and we have here nd square. So we take from nd square this square as a common factor. What is left from nd square after we took from it this square as a common factor? What is left is actually n. Okay, so we have here this square and times m plus n plus, here we take m times n as a common factor. What is left from n times m square after we took from it nm as a common factor? What is left is actually m. And what is left from mn square after we took from it mn as a common factor? What is left is actually n. And it is equal to b squared times m plus c squared times n. So here we take out a common factor of m plus n from those two expressions, and we'll get that according to equation number 3, m plus n inside the brackets. What is left from this square times m plus n after we took from it m plus n as a common factor? What is left is actually this square. What is left from m times n times m plus n after we took from it m plus n as a common factor? What is left is actually mn, and is equal to b squared times n plus c squared times n. For the domain, we can see that line segment m plus n equals to a. Why? Because of the fact that the length of side BC equals to a units, and BC equals to BD, that is m, plus DC, that is n. So BD equals to m plus n, and it is also equals to a. So we substitute m plus n by a. Okay. in equation number 3, and we'll get that according to equation number 3, m plus n is a, so we'll substitute m plus n by a times d squared plus m plus n equals to b squared times m plus c squared times n. Okay, and this equation is Stewart's theorem. You see here, Stewart's theorem, b squared times m plus c squared times n equals to a d squared plus mn. Here, b squared times m plus c squared times n equals to a d squared plus mn. So we actually succeeded to prove Stewart's theorem. In the next step, I will summarize the lecture. So, in this lecture, we proved Stewart's equation. In a nutshell, Stewart's equation yields a relation between the side lengths of a triangle to its Cevian. The Cevian here is AD. Repeat again. In a nutshell, according to Stewart's theorem, yields a relation between the side lengths of the triangle to its Cevian. The Cevian here is AD. And according to Stewart's theorem, b squared times m, b is the length of side AC, so it is b squared times m, is m is the left side, the length of side BD, this side, again, BD is the length, m is the length of side BD. I repeat again, m is the length of this side length of side of line segment BD. Again, BD is the length, m is the length of line segment BD. Again, m is the length of line segment BD, and n is the length of line segment DC. So, I'll repeat again, b squared times m plus c squared times n equals to a d squared, this is the length of the Cevian squared, plus m times n. So, I will copy again the triangle. Without all the additions. So this is triangle ABC, and the CVN exists from point A, and it touches side BC at any point. Okay, so this is the CVN. Repeat again, this is the Cevian. So, Stewart's theorem yields a relation between the side lengths of the triangle and its Cevian, the Cevian AD. And we know that the length of side AB equals to C units, side AC equals to B units in its length, side AD equals to D units in its length. AD is the Syrian of triangle ABC. Side BD equals to M units in its length, and side DC equals to N units in its length. Then, according to Stewart's theorem, B squared times M, B squared times M, B is the length of side AC, so B squared times M, M is the length of line segment BD, plus C squared times N, C squared times N, N is the length of line segment DC, and C is the length of side AB, equals to, and here BC equals to A units in its length. So it is equals to A, it is the length of side BC, and we open the brackets. Inside the brackets we have D squared, that is the length of the Syrian squared, plus M times N. M times N. Okay? We actually proved this equation, that B squared times M plus C squared times N equals to A, we open brackets, inside the brackets we have D squared plus M times N. Here we close the brackets. Okay, so this is what we proved here. We proved this equation by doing a construction here. From point A, we draw perpendicular on BC. Again, from point A, we draw perpendicular on BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC as E. Okay? And then we implemented the Pythagoras theorem in this green triangle, triangle AED. We actually defined side ED as X. We defined side AE as H. And here BE equals to BD minus ED. Again, BE equals to BD minus ED. BD is M, ED is X, therefore BE equals to M minus X. Okay? And finally we found out also that line segment EC equals to X plus N. It is very easy to see that EC equals to X plus N. In the next step, we actually implemented the Pythagoras theorem on the green triangle, triangle AED. This right green triangle AED, according to the Pythagoras theorem, AD square equals to AE square plus ED square. Repeat again. AD square equals to AE square plus ED square. Okay. AD equals to D units in its length, so we substitute AD by D, therefore AD square is D square. AE equals to H, therefore AE square is H square plus ED square. ED equals to X units in its length, therefore ED square is X square. X square. So in conclusion, we found out that according to the Pythagoras theorem, in the right green triangle AD, D square equals to H square plus L square. In the next step, we focused on the right triangle, triangle AC. On this right triangle, triangle AC, we implemented the Pythagoras theorem. The square of the hypotenuse equals to the sum of the square of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC square. And it must be equal to the sum of the squares from the perpendiculars. That is to say, it must be equal to AE square plus AC square. Repeat again, in the right triangle, triangle AC, according to the Pythagoras theorem, AC square equals to AE square plus EC square. AC equals to D units in its length, therefore AC square is D square. AE equals to H, therefore AE square is H square. And finally, EC equals to X plus N units in its length, therefore EC square equals to X plus N square. In conclusion, we found out that according to the Pythagoras theorem, B square equals to H square plus X minus N square plus X plus X plus N square. Repeat again. According to the Pythagoras theorem, in the right triangle, triangle AEC, B square equals to H square plus X plus N square. So B square equals to H square. We open the brackets. X plus N square equals to X square plus N square plus 2xn. And here we have already found out that H square plus X square equals to D square. So we can substitute H square plus H square plus X square in this equation number 1, by D square. We did it here and we found out that B square equals to D square plus N square plus 2 times xn. Okay, this is equation number 1. Okay, and then we implemented the Pythagoras theorem in the pink triangle, triangle ABE. In this pink triangle, triangle ABE, according to the Pythagoras theorem, AB square equals to BE square plus AE square. Repeat again, according to the Pythagoras theorem in the pink triangle, triangle AED, triangle, according to the Pythagoras theorem in the pink triangle, triangle AED, in the pink triangle, triangle ABE or AEB, AB square equals to BE square plus AE square. Again, AB square equals to BE square plus AE square. Okay, AB square equals to BE square plus AE square. AB equals to C, therefore AB square is C square. And it is equal to BE square. BE is M minus X, therefore BE square is M minus X square plus AE square. AE is H, therefore AE square is H square. So in conclusion, we found out that C, according to the Pythagoras theorem in the right pink triangle AB, C square equals to M minus X square plus H square. So C square equals to M minus X square equals to M square plus X square minus 2 times MX plus H square. So we have C square equals to, we have already found out that H square plus X square is this equals to D square according to this equation. So we substituted X square plus H square in this equation by D square and found out that M square plus D square minus 2mx equals to C square. This is equation number 2. According to equation number 1, we found out that B square equals to D square plus N square plus 2nx. In the next step, we multiplied equation number 1 by m. Then we multiplied equation number 2 by n, and then we added the two equations together. Okay? So here we multiplied the equation number 1 by m. So that is to say it is m. In this side of the equation we have m times d square plus n square plus 2 times nx. And then we multiplied the equation number 2 by m. Equation number 2 we multiplied by n. So it is n times m square plus d square minus 2 times mx. again we multiplied the equation number 1 by m, we multiplied the equation number 2 by n, and then we added the two equations with each other. This gives us equation number 3. Then we multiplied the other side, the left side of equation number 1 by m, and multiplied the left side of equation number 2 by n, and then we added the two equations with each other. Here we multiplied the equation number 1 by m, we multiplied the equation number 2 by n, so it is nc squared. Here it is mb squared plus nc squared. So this is equation number 3. This is the multiplication of equation number 1 by m, the multiplication of equation number 2 by n, and then the addition of two equations with each other. So this is equation number 3. And then we open the brackets here. We have m times d squared is md squared, plus m times n squared is mn squared, plus m times 2nx is 2mnx, plus n times m squared is nm squared, plus n times d squared is nd squared, plus n times minus 2mx is minus 2mnx. It is equal to mb squared plus nc squared. So this is what we got, equation number 3, after we open the brackets. md squared plus mc squared plus 2mnx plus nm squared plus nd squared minus 2mnx equals to b squared m plus c squared n. So here we have plus 2mnx minus 2mnx is 0, so those two expressions will get cancelled. What is left from equation number 3 after we cancel the two expressions that are equal to each other? What is left is that here we have d squared. We took d squared we take out d squared as a common factor from md squared and also from nd squared. So we took out d squared as a common factor from md squared. What is left from md squared after we took from it d squared as a common factor? What is left is actually m. And what is left from nd squared after we took from it d squared as a common factor? What is left is actually n. So in conclusion, found out that d squared times m plus n equals to, here in the next step we took mn as a common factor from mn squared. What is left from mn squared after we took from it mn as a common factor? What is left is actually n. And what is left from nm squared after we took from it nm as a common factor? What is left is actually m. So in conclusion, we found out that mn squared plus nm squared equals to mn times m plus n. And it is equal to n to b times m squared plus c times n. Okay. Here we take out m plus n as a common factor from those two expressions. So inside the brackets we left with, from this expression, d squared, and from this equation m times n. So in conclusion, those two expressions are equal to m plus n, and inside the brackets we have d squared plus m times n, and it is equal to b squared times m plus c squared times n. According to what is given us in the drawing, it is very easy to see that here, it is better to see it here. It is very easy to see that m plus n equals to a. The length of side BC is a, and a equals to BD plus DC. And therefore it is equal to m plus n. So a equals to m plus n, so we substitute a, we substitute m plus n by a. Here we substitute m plus n in this equation, this Stewart's equation, by a. And we got here that a times d squared plus m times n equals to b squared times n plus c squared times n. And that is actually the Stewart's theorem. We actually succeeded to prove Stewart's theorem. Okay, thank you very much.